Hello everyone. So this is the first lecture in our 370 course. You can follow along with the lecture notes and the PowerPoint slides that I supplied on Canvas. So the purpose of this lecture is to help you understand where the elements on the periodic table, how they came to be. And so what we'll do is we'll start with elementary particles, form lighter elements, and then from those elements form the heavier elements that we see on the periodic table today. And so we'll start with the Big Bang Theory, which you should just think of as a mathematical model. And so it describes what we've observed in the universe since the beginning. Now, the mathematical model, it breaks down once you get very, very, very close to zero, time zero. And as mentioned in the notes, that's at about 10 to the negative 43 seconds. And then it just does not make sense anymore. So we really don't know what happened at the very beginning. But what the model assumes is that the universe was a singularity at the beginning of time, meaning all the mass and energy of the universe was in a space the size of a pinpoint. And then at some time and some reason, about 15 billion years ago, it became unstable and blew up. And so this raging fireball full of elementary particles and photons just started to expand into empty space. And so in the paper, we also have the paper I asked you to look at and read. We have some figures, and it lists the different elementary particles that we're talking about in this initial fireball. And so we're talking about nucleons, which includes protons and neutrons. We have leptons, which are electrons, positrons, neutrinos, antineutrinos, and also photons, which photons we know also as light. These particles, they behave as waves and they behave as particles. So this table also has the charge and the mass of all of these particles. The, the particles that have significant mass are the nucleons. The electrons and others have very little mass, relatively speaking. And so again, within this initial fireball, there's probably lots of reactions that can occur. Here I have just two examples to kind of show you the notation that's used in particle physics. And so we have our proton here, which is just a hydrogen atom with one proton in it. We have our electron, our neutrino, antineutrinos, positrons, which are the same as an electron, but with a positive charge, and neutrons. And so these are balanced equations. The top row of numbers, that signifies the mass. And so again, it's the nucleons, like protons and neutrons, that have significant mass of 1. We round the number. And because neutrinos and electrons have relatively less mass, we just call those zeros. But we're kind of keeping track and balancing on both sides of the equation, the mass. And then at the bottom here, this is how we balance the charge. And so neutrons, of course, have no charge. Protons have a +1. Electrons have a -1. But if you look on both sides of the equations, Each side is balanced with respect to mass and charge. And so after 1 second, the temperature of this fireball is 10 to the 10. That's 100 times greater than our sun. After a few minutes, it's down to 10 to the 9, a billion Kelvin. And again, it's expanding at the speed of light into empty space. And so, at this time, under these conditions at a billion degrees Kelvin, we actually start to get reactions where fusion is occurring. So fusion is just where smaller particles end up coming together and making heavier particles. So in this first reaction is an example of a neutron and a proton coming together to make deuterium and a gamma ray. A gamma ray is just a photon, but this is necessary in order to balance the reaction in terms of particle physics. There's other things we need to consider in terms, rather than just mass and charge, there's also energy that we need to balance. And this helps balance the energy portion. The deuterium can continue to fuse with nitrogen to create tritium, which is another isotope of hydrogen. We use the word isotope, sometimes we use the word nuclide. So this is also considered a nuclide. Each of these steps are releasing energy in the form of light. And then here we see the formation of helium during this fusion process in this huge fireball. And so even today, 98% of the atoms that are in the universe are either hydrogen or helium. And they make up the large portion of what we would see in the stars in the heavens. And so after 3 minutes, this fusion of particles at high temperature and high pressure, it stops because the fireball starts to cool so much that we just don't have enough temperature to create that fusion. So this is expanding into empty space. We are now cooling, but there's other factors, there's other forces in the universe that are at play. And the force that starts to continue the fusion process is gravity. So we have this matter, and we know that the force of gravity is where things with mass are attracted to each other. So these clouds of cosmic dust, they begin to attract because the particles are attracted to each other. And in doing so, they start to increase in temperature and pressure. Because remember, this hydrogen is a gas. And so at that point, at certain temperature, it begins to ignite. And that's the beginning of star formation. And then at that point, once it ignites, fusion occurs. So in a star, and I should say I had to move because our local star came out of the clouds. And so now we are in the sun. But in a star like the sun, we have this balance between the heat of fusion. These reactions that we're talking about here, they release heat and energy, and that's an expansive force. And that is balanced with the force of gravity, which is trying to take these particles and contract and actually press them together. So this is a balance. And so here we have reactions, examples of reactions that are occurring in our sun right now to form helium. our sun is a young star, so it's helium fusion that's occurring at about 10 to the 7 to 10 to the 8 Kelvin. And so as we go along from here with the helium formation, think of fusion as the formation or the of having lighter nuclei combined to create more massive nuclei. And so that is where our star, our sun, is at. But in a couple billion more years, that hydrogen fuel will run out. And so we'll no longer have hydrogen fusion creating helium. What we'll have is a star that begins to actually use helium as a fuel source. And so once it's done with the hydrogen, the star will begin to collapse due to gravity, but then that will increase the temperature and the pressure to about 10 to the 8. And that will then begin and create conditions, I should say, that would allow for helium fusion. And that is an example of a red giant star, which if you looked out in the evening sky, you would see some stars that have more of a reddish tinge. A good example is Betelgeuse. If you want to look up that star, it is a star that is at the end of its life, and I believe it's considered a red giant. So in these stars, what we have is helium fusing together to create heavier and heavier elements. And what we're starting to see is this pattern where now we are actually creating elements that are on the periodic table, and we can start to think about the abundance of some of these elements like carbon and oxygen in our solar system and how that came to be. So this process continues until we get to iron 56. So to end this part of the story, we started with the fireball and then the cooling of that fireball with then the interaction of the cosmic dust with gravity, which then started this process again, which started hydrogen burning, as shown in the paper on canvas, where you create deuterium, tritium, and then also helium in the process, to then a star that fuses helium and uses helium as a fuel for the expansive force, which creates the heavier elements, well, I should say lighter elements on the periodic table, but heavier elements within the star. And we do that until we reach a point where fusion is no longer a expansive force. And so what occurs in these red giants is essentially the iron 56 forms and stays within the core. And at that point, there's no energy gain through the fusion of iron 56. That's why iron 56 is at the apex on this graph. That's iron 56 there. And it's due to the fact that if you fuse something with iron 56 nucleus, if you fuse it, it's actually an endothermic process, meaning it takes energy to actually get that to happen. Up until this point, all these fusion reactions were releasing heat, releasing energy. But again, at this point, that is no more. And so iron 56 is considered the most stable nuclei on the periodic table for this reason. And so at this point, we're going to stop the story. You can digest this video. And at this point, this is a critical point for the star, and there's lots of ways in which the star can go in different directions in terms of either becoming a um, you know, black dwarf, it become a neutron star, it can explode in a supernova, or if it's massive enough, it could even turn into a black hole. But this is one of the final stages of the star's existence.